Hello, my name is Brittany, and in this video, I will be walking you through the Bayesian analysis approach to the two-sample normal model. Our goal is to compare two normal populations. Typically, this is done by comparing the means of two samples from the two normal populations. We can then use the same Bayesian techniques used for the one-sample normal model to obtain priors for the parameters of the two populations. We will then use this information for the priors and the data to construct posterior distributions for our analysis. Our data comes from two independent samples, both of which come from normal distributions. The commonly used reference prior is the improper density 1 over tau 1 times 1 over tau 2, where tau 1 is 1 over the variance from sample 1 and tau 2 is 1 over the variance for sample 2. This is an improper reference prior that does not integrate to 1. However, it is useful because it allows the posterior joint distribution of mu and tau to be obtained in closed form. Another approach to prior selection would be to use independent proper priors. Instead, mu1 and mu2 follow normal distributions, and tau1 and tau2 follow gamma distributions. When using these proper priors, the posterior joint distribution cannot be obtained in closed form, so we have to use a Gibbs sampler to obtain the proximate draws. The hyperparameters A, B, C, and D can be determined by utilizing expert opinion and asking them specific questions. We'll discuss this in more detail now. To find the normal prior for mu, we have to ask the expert what their best guess for mu is. Then we set the prior mean to be A, which is the expert's best guess. Then we can ask the expert for the largest reasonable value for mu, or more specifically, a value only 5% chance that mu would exceed it. This gives us the 95th percentile of the prior distribution. After that, we can solve a 2x2 system of equations to obtain the A and B pair. Finding the hyperparameters for tau is a little bit more difficult. To find the gamma prior for tau, we ask the experts about sigma or about a percentile of the data. Then we translate that information back into statements about tau. Since mu are assumed to follow a normal distribution, we know the percentile equals mu plus z alpha times sigma. Since mu equals A, we know that sigma equals the percentile minus A divided by the z-score at alpha. If we're looking for the 95th percentile, D over C plus 1 equals the percentile A z alpha squared. We then solve a system of 2x2 equations to obtain C and D. To approximate the posterior density draws, we will use the Gibbs sampler with two components. The Gibbs sampler samples from the conditional densities of tau given mu and y, and the conditional density for mu given tau and y. As noted here, we start by selecting a starting pair for mu and tau. Then we generate the next values for tau from a gamma distribution, as shown here. Next, we generate mu from the normal distribution, as noted here. Now let's look at an example to see how these ideas are utilized with real data. For this example, we want to test whether a diagnostic assay, Diasroin, is able to distinguish between patients with low bone turnover versus those with normal bone turnover. The example uses 34 kidney patients who are identified as low or normal using a different type of test. Then Diasroin was used to determine if it could correctly identify the patients. We read in the data for the low and normal groups with this R code, and next we're going to want to visualize the data to see the type of data we're working with. In the upper left-hand corner, we have a box plot of the untransformed data. It's pretty clear that the data does not appear to be normally distributed. After we perform a log transformation, however, on the data, we have the box plot on the right-hand corner. The data appears to be normal. To investigate this further, we can look at the QQ plots for the log transformation of the low and normal groups, and because the data seems relatively close to the line, we will assume approximate normality. Now we need to decide what type of prior distributions we want to use for our analysis. The experts provide the following information to help us determine the parameters for mu. He says the median for the low bone turnover group is believed to be 130, and he says he's 95% sure that the median is less than 142. He also says that the median for the normal bone turnover group is believed to be 220, and he is about 95% sure that the median is 240. We can use this information as well as some R code to help us determine the hyperparameters labeled here. This fine normal R code allows us to solve the 2x2 system of equation with our expert's opinion. We see that for the low group, the mean is about 4.9 and the standard deviation is about 0.05. For the normal group, there appears to be a mean of 5.4 with a standard deviation of 0.5. Now we can plot the normal priors for the density of mu for the low group and mu of the normal group. To find the prior on tau, the experts gave us the following information. His best guess for the 90th percentile of the Diasroin value for the low turnover group is 170, and for the normal group is 280. We then use R to solve the 2x2 system of equations to determine our two hyperparameters for tau distribution for the low and normal groups. Like mentioned earlier, we need to transform the data from the information on the standard deviation to gain information about tau. This R code allows us to use the expert's information on the 90th percentile to calculate the hyperparameters to use in the tau distributions for our analysis. Now that we've obtained the hyperparameters for tau and sigma prior distributions, we can make some plots. These plots let us visualize the prior distribution for both tau and sigma for both the low and normal groups. After we obtain the appropriate priors for mu and tau, we can use the Gibbs Sampler to obtain the approximate draws for the posterior densities. The Gibbs Sampler draws from the conditional densities of tau and mu to approximate the posterior densities. These conditional densities are based off of both our data set as well as the prior distributions. After running the Gibbs Sampler, we obtained the following plots for the posterior densities of mu and sigma for the low and normal groups. The difference in the mean of the low group and normal group can be of interest because it allows us to compare the means. Looking at the summary output in R, we're 95% sure that the mean difference, mu normal and mu low, is between 0.41 and 0.67, with a mean of 0.55. This leads us to conclude that mu low is less than mu normal. Now let's consider predicting a new observation. To find the density for a new observation in the log scale, we run the following R code. For new observations in log scale, we're 95% sure that it will be between 3.4 and 6.4 with a mean of 4.9 for the low group. And then for the normal group in the log scale, we're 95% sure a new observation will be between 4.3 and 6.5 with a mean of 5.4 for the normal group. It's often more practical to talk about the predictive densities in the original scale, since this is what our experts are familiar with. When talking about the untransformed data, we are 95% sure a new observation of the score for the low group will be between 11.41 and 446.3, with a median of 128.6. For the normal group, we are 95% sure that a new observation of the score will be between 48.4 and 554.1, with a median of 222.2. That's the end of our discussion on the Bayesian approach to two sample normal models. The information here and more in-depth information can be found in the book Bayesian Ideas and Data Analysis. Thanks for watching!